White light, when cast in a prism, separates into all colors in the RGB, because white light reflects all colors. On the other hand, the light emitted by the hydrogen gas emits only certain wavelengths in the atomic emission spectra. So this is what we call the line spectra. So once you pass the light emitted by the hydrogen gas in a prism, only certain wavelengths can be seen in the atomic emission spectra compared to the white light where it reflects all the colors in the RGB. Now this atomic emission spectra derived from the visible light became Balmer's basis to deduce the following formula for the wavelength of the spectral lines. So this n is equal to 2. So b is a constant having the value of 364.6 nanometers. So b is equal to 364.6 nanometers. Balmer's equation was later found to be a special case of the Rydberg equation, formulated by Johannes Rydberg. So Rh is the Rydberg constant for the hydrogen atom. So the Balmer series uses n is equal to 2 and m is greater than n. So what will be our observation on the atomic spectra? So the atomic spectra consists of only limited number of well-defined wavelength lines, suggesting that only a limited number of energy values are available to excited gaseous atoms. So this is an evidence of the quantization of energy in the subatomic world. This provided insight into the quantum theory. So now what makes different elements emit light of different colors of wavelengths? Bohr answered these questions through the Bohr model of the hydrogen atom. So, according to Bohr, he stated that the potential energy of an electron is also quantized. It can only inhabit certain energy levels at fixed distances from the nucleus. So, it can only inhabit certain energy levels. So, once a photon, or a photoelectron, once a photoelectron is emitted, due to one electron going from a higher energy level to a lower energy level, that energy, delta E, is also quantized. It can only inhabit certain energy levels at fixed distances. So, this electron cannot move in here in the middle. It can only inhabit certain energy levels. So an electron will transition from one energy level to another when a photon of specific energy, for example, this is the photon of specific energy, is absorbed or emitted. So an energy photon will correspond to the difference between energy levels. Each gaps have different transition energy. So the energy levels are expressed in this equation. This is the equation. E sub n is equal to negative RH over n squared. Based on the equation, the energy is quantized or restricted to specific values, and that all the allowed energy values are negative. As you can see, n is only equal to 1, 2, 3, or the set of integers, positive integers. So the equation tells the energy level of an electron, this, denoted by E sub n. But we usually measure the change in energy of an electron during the transition. So we usually use the Rydberg equation, which is this. So the energy of the photon can then be used to solve the frequency and wavelength of the emitted light. We group the transitions based on the energy level that they land on. So n is equal to 1, as you can see for the Diliman series, n is equal to 2, as you can see for the Balmer series, n is equal to 3 for the Paschen series. So the Balmer series happened to contain transitions that contain photons of visible light. As we said earlier, Balmer used the atomic spectra for the hydrogen in the visible spectrum. So he used the visible part to formulate his equation, which is this. So each element has its own atomic spectra, just like a fingerprint, because each element has a different nucleus. So this line spectra is unique only to the hydrogen. So two different elements cannot have the same atomic spectra, just like